Okay, class, now we have an opportunity to talk about that other type of bonding known as covalent bonding. And so you might recall from the first video that covalent bonding involves two or more species, these species likely to be nonmetals, and they end up sharing electrons. And this is different from our ionic bonds, which transferred electrons. And so to think about covalent bonding, we can imagine we have two atoms that are far apart. And we can take those two atoms, let's say that these are two hydrogen atoms, so off to the right here. And when we take those two atoms and we bring them closer together, as we bring them closer and closer together, what happens is now the electrons from one atom can start reacting, or not reacting, but interacting with the protons from another. And so what occurs in the first place is that electrons and protons um, from each atom slash nuclei interact with each other. And that interaction is energetically beneficial because you have a negative particle interacting with a positive particle. So you have that Coulombic attraction that leads to lower energy. And as you bring these two atoms closer and closer together, and you start to maximize that attraction, you reach a distance at which there's optimal interaction of the charged particles where there's the peak amount of attraction with the lowest amount of repulsion from having a proton from one nucleus close to the proton of the other nucleus, or the two electrons too close to each other. So we'd say at optimum separation, a bond is formed. And this bond that's being formed is going to be characterized by, so in the bond, in this bond being formed, it's going to be characterized by electrons are shared by each atom. And that's to say that in this case, each of these hydrogens started with their own electron. And when they come together, now they're sharing both the electrons equally. And so electrons are shared by each atom, and parent atom no longer owns the electron. So the important thing here is that the electrons are being shared within a bond. And in these species that are covalently bound together, that have this sharing of electrons, these species behave as a unit, not individual atoms. So when you take, not individual, so when you take these two hydrogen atoms and bring them together, they now are not two distinct species. They're no longer a hydrogen and a hydrogen that can, separate from each other. They're now permanently stuck together until you do some chemical change. So you have these two hydrogens that they're always going to float together as a unit. There's always going to be two hydrogens together. And the same is true when you take a hydrogen and a fluorine and you're bringing them together, or two hydrogens and an oxygen. They come together and they stick to each other, and they don't separate through physical means. You'd have to chemically alter them to get the two atoms from the separate elements to separate from each other, or the two atoms of the same element in the case of H2. And so these substances that have covalent bonds, we would say that these species exist as molecules. And if we think back to our first lecture, that means that they are pure substances. They're composed of one type of molecule. And this is as opposed to our ionic compounds, because ionic compounds, when we think about those in, as a single crystal or what have you, the ionic compounds are actually this large lattice. It's not just a single sodium and a chloride together. Instead, it's, this whole 3D structure of sodiums and chlorides. But with covalent substances, you have distinct water molecules. So if you have a glass of water, so glass of water is many distinct water molecules. And this is as opposed to the array from our ionic compounds. So as opposed to array of ionic compounds. And so we can still say that, sodium chloride is a pure substance. It's a sodium chloride unit. But when we think about that sodium chloride, it's not distinct water molecules. It's this whole lattice of sodium and chlorine ions together. So this is what chemical bonding looks like, a sharing of electrons. And when we think about naming a covalent compound, we have to make sure that we actually have a covalent compound. And this means that this means we are looking for two or more nonmetals. So if we have a metal present, then we likely don't have a covalent compound, except in the case of our polyatomics, because that polyatomic itself is covalently bound, and then it's forming an ionic bond with the metal. And so it has covalent character and ionic character because it's two separate things. We're thinking about the bond between the atoms that make up the covalent compound and then the two ions that make up the ionic bond. But let's just focus right now on the covalent compound alone. And so when we have something that only contains these two nonmetals, we're pretty sure now we have a covalent compound. And when we name these, we're going to start by naming, each of our separate species. And in this case, what we end up doing is we have to specify how many we have of each different atom/element. And so we start with the leftmost atom. And so let's say we have something like NO2. To describe how many of the leftmost atom we have, we usually denote a prefix. And in this case, the prefix that we would expect to apply here is mono, because we only have one. But whenever you only have one of the first element, we omit that mono prefix. And so the way we'd name NO2 is we'd first start by saying nitrogen, because we omit the mono prefix that we will see is different when we name different compounds. So I'm showing three different compounds composed of only nitrogen and oxygen. We'll name the first one, and then we'll step through the other two. And so now that we have that first nitrogen, we have the name of our first element, we've completed this green box. Now we have the second part. So we have to do the prefix, which describes the number of our second element, and then we put IDE. And so our second element here is oxygen. And so here we see we have two. So we look up two right here, we have di. So we put di, and then we put oxide, because we have the base name for oxygen is, we have oxygen. And then we saw that our base name was we cross out YGEN, and we put IDE. So the same as when we did our ionic compounds. So we'd call this first species nitrogen, no prefix because we only have one, dioxide because we have two oxygens. If we go to this next example, we have NO. So once again, we have a single nitrogen, and in this case, we have a single oxygen. So we don't have to specify the mono for the single nitrogen, so we'll say nitrogen. And then for the oxygen, now we have one oxygen, so we'll say monoxide. And so you might imagine that instead it would be monoxide, doubling the O's from mono from the prefix, and then oxide from the base name of the second element plus IDE. But to avoid, too many vowels consecutively, we get rid of one of those O's to give us monoxide. And then in the final example, we have N2O. And so here, because we have more than one of the first element, we do apply a prefix. So we have two nitrogens, so we'd say Di for 2, name of our first element, nitrogen, and then the prefix for our second element, which we have mono for 1 oxygen, oxide for the base name of our second element. So each of these is nitrogen plus oxygen, but you can see that we can have many different forms, and we have to specify that by saying how many of each atom we have. And so what I'd like you all to do is to pause the video right here and try to either name the compound in the first 3 instances, or provide the formula for the following 3 that are numbered 4, 5, and 6. Okay, so pause the video here and then we'll come back. All right, welcome back. And so in this case, I actually gave you compounds that were only covalently bound. So you didn't have to do that first check to see if you only have nonmetals, but you can still do that and see that in the first case you have nitrogen and iodine, the second you have phosphorus and chlorine, the third phosphorus and sulfur, fourth phosphorus bromine, fifth nitrogen and oxygen, and sixth sulfur and fluorine. And so all of these are on that right side of our periodic table and they're only nonmetals. So when we name these in the first 3 instances, we follow the scheme we just outlined on the last slide. So we start by naming our leftmost atom, and if we only have one, we don't have to put a prefix. So here we have nitrogen, and then we specify our prefix. 3 is tri, and then this is one of those cases where we drop one of the vowels because this is iodine and its base name is iodide. We don't want to put 2 i's close to each other, or rather, typically we drop a vowel, but in this case, you can drop or keep it. I'll keep it. So you have triiodide. So forget the fact I talked about dropping the i's. Let's keep them in this case. Let's only drop vowels if we have things with the oxygen. Okay? And so in our second case, now we have phosphorus with chlorine. And so this is triiodide. Okay? We only have one phosphorus, so we can name that normally. So just phosphorus. We have 5 chlorines, so that's penta. And then we have the base name of our second element is chloride. So this is phosphorus pentachloride. And then finally, we have this compound right here. And because we have more than one of the first element, we specify how many that is. So we have tetra for 4, phosphorus for the name of our first compound. And then we have 10 of our second, so that's deca. And then we put the base name of that, which is sulfide. So base name plus IDE. Okay. Now we can write the formulas for the last 3. So we have phosphorus. There's no prefix that comes before that, so that must just be a single phosphorus. And then we have 3 of bromide. And so bromide is, the base name of bromine plus IDE, and we put 3. So that's PBr3. The second one, we have 2 nitrogens. So dinitrogen means N2. Pentoxide means that you have oxygen is oxide, and you have 5 of them. And then our final one, we have sulfur. There's no prefix here, so that must mean there's a single sulfur. Hexafluoride, fluoride is fluorine. And then we have 6 from hexa. And so that's how we would write the formula for sulfur hexafluoride. Okay? And so that kind of leaves us with the following scheme that can help us when we're naming whatever we have. And so if we're given a compound, the first thing we want to ask ourselves is, does this contain a metal? If yes, then we know that we have an ionic compound. And then we're going to name it based off of if we have, the metals that have variable names and the metals that have the non-variable names. So if you have a metal that's group 1, group 2, aluminum, silver, cadmium, or zinc, that means these are your non-variable metals. And then you're just going to check if you have a polyatomic or not. And so these ones, there's no Roman numerals because you're very certain about the charge on your cation. So this is no Roman numeral. If instead you have a metal that isn't one of the group 1, group 2, or the ones that are specifically named, that means you have a cation that can change its charge. And so here, you have to include a Roman numeral. So you have include Roman numeral. And then if, when you do that first check, you don't have a metal, the next thing you ask yourself, is the compound an acid, which means that you either have H listed first in the formula, or you see that you have AQ as part of that formula. If yes, then you do have an acid, and you have to decide if it's an oxoacid, meaning it contains oxygen. So in that case, you do the ite to ic, ite to us. Or if you don't have this H listed first, and you don't have this aqueous state for that, then you have a normal, a normal covalent compound, and you just name it using that prefix plus name of first atom plus prefix plus base name of second atom plus IDE. And so this just summarizes what we've talked about to this point. And then we'll end this part of this video by talking about, why do bonds form? And so at the first of when we first talked about these bonding, we said it's all about getting that energetic stabilization. In most cases, we think about, it's this attractive force that provides stability. And so in the case of ionic bonds, the reason the bond forms is that you're allowed to take advantage of that Coulombic force. So allows for attraction of your oppositely charged ions. And so we formed the bond because when we're able to take a positively charged ion and a negatively charged ion and bring them together. So brings together pos ion and negative ion. And that Coulombic force that they each experience with each other, we said that they form this lattice, so we call that attractive energy. So this attraction, we're going to call this the lattice energy. So this lattice energy is the Coulombic attraction, or the attraction that comes from the Coulombic force / attraction. In the case of covalent compounds, the reason that we have bond formation is that the energy of the system is lowered. And that comes from the interaction of the subatomic particles with each other. So system is lowered. And really, this all boils down to having the most stable or lowest energy state. In the case of covalent compounds, that's you get the lowering of energy by allowing electrons from one atom to interact with the protons of the other. In the case of ionic compounds, you go from repulsion of similarly charged particles, so calcium cations with calcium cations, to the attractive force of calcium cations with chlorine anions. So energy of the system is lowered by formation of bond. This comes from subatomics interacting from one atom to another. And like I said, that's, the electrons on one atom interacting with the protons from another. And so, all boiling down to the most stable, lowest energy state. Okay, and so in our final video lecture, we're just going to talk about how we can think about, utilizing, now that we have these descriptions of what these molecules and forming units look like, we can think about weighing them out and then depicting them for our viewing pleasure.